Today on Vino Diladon, I bought myself a laser corpse to experiment with from one of my favorite sellers, Starlight Photonics. Links below in the description. He has a few of these at the time of making this video. And which one did I choose? Number 13. And we're going to make this thing live again. Let's open it. That's a good label. When I die, bury me in this stuff, because I'll last forever. Darn shame too, it's a nice ESD bag. Aha, and now it's a good ESD bag once again. Alright, so this is a Uniphase microgreen. I think it's a 4301-010, 10 milliwatt, 532 nanometer GPSS laser. And this particular laser has a bad pump diode in it, or at least he said it was an open pump diode in the listing. So I'm hoping maybe it's a wiring problem. Of course, the only way we're going to figure that out is to get inside. Looks like nobody else has been in here. Seal is not broken. So let's go ahead and get some tools out. We need metric or standard. Metric or standard. Let's try metric. It was made in America, wasn't it? I see. Well, now I gotta find the standard stuff. Why do I fix so much European and China things? Uh-huh. Alright, it's time to go and get the wrong tools. But apparently, that's what I need. Don't worry, folks. We'll get inside of this laser, no problem. And the nice thing about this laser is because it's a project laser, I don't even have to get it back together. That's what makes it an entertainment laser and not a work laser. Try this. Mental note to self. Pick up standard Allen wrench from store. It is, yes? Oh, come on. Talk about being up a river without a paddle. At least I nailed the intro. Alright, so I'm expecting to find some goodies in here. This particular one I paid, what, $27 plus $15 in shipping, so about $45. And it's definitely worth it for me because inside there's a couple of things that definitely make this worth the value. There's 2 thermoelectric coolers inside of it. It has a good, at least monolithic crystalline assembly in it. And hopefully a resonator. I am destroying that bit. I should put some spoilers on the back of my screwdrivers to give me extra downforce. I removed everything but the sticker I want to remove. Come on. Oh, wow. There isn't much in here at all that I can see. It's a really interesting assembly inside. Okay, so see what we have. We have the DB14, DB15, DB14. On the back, we have a photocell right here, photodiode that'll detect how much light is leaving the laser for feedback. One thermoelectric cooler here, another little thermoelectric cooler right here. Those look like they're 20 millimeters. I guess they're 5 volt up to 5 amp thermoelectric cooler, so pretty beastie. It looks like we have a separate resonator, so I'm going to bet that inside of this area right here, we're going to have a C-mount 808, probably near half watt, and after that we're going to have either the YAG or the vanadate with the neodymium doping. This front panel right here, this copper block, looks to be the output coupler, so that means that inside we shouldn't have a monolithic crystalline assembly that joined 2 crystals, a KTP and whatever neodymium doped crystal it is, but we're going to have 2 separate crystals, and that's going to be useful. That way we can play around with them. But since it has a bad pump diode, I want to get to that. I want to see if the pump diode is what's bad, or if it's possibly the wiring. I hope it's the wiring. More standard screws to contend with. All right. Let's see what's the way to go about this. Yeah, I'm gonna remove this block right here. So let's see. Looks like I can just pull the whole unit out by undoing these 4 screws right here. I'm almost certain that that's going to be a C-mount laser diode on the inside of that. I don't have any spare C-mounts if it's a 9mm that I do have. Alright. First try. Alright, now we're getting somewhere. Well, we have the whole resonator assembly now pulled out. Let's see, yeah, that's definitely the output coupler window. I want to take this off, but then I know realigning it's going to be a nightmare if it's a resonator. And I know my pump diode is in this block right here. Oh, is that loose? Oh, no, I'm just feeling the graphite on the bottom. Alright, looks like I'm going to have to undo these screws. And these screws right here, if I can get to the pump diode section. Alright, with those 4 screws removed, let's go ahead and see if we can remove that assembly and get to the pump diode. Now we got a couple of things here. So I got the wires for the thermoelectric coolers, red and black. These 2 smaller wires right here on the bottom. That's one of the thermistors for the resonator. We have another one of those thermistors too. Yep, right here in the back. So that's the pump diode thermistor, and these are the thermoelectric cooler wires going to here for the pump diode temperature. Anyway, let's see if this comes apart now. It does not. Oh, it's glued. I bet you that's why. Alright, so now I need to figure out how to carefully break that bond. Go ahead and fully remove the other side though. No, just some mechanical force and should come apart. Yeah. Alright. Now what do we have? Alright, so this is the side that goes into the resonator. You should be able to see some pink light through there. So it could very well be a monolithic crystalline assembly in there. Let me take a close look at that. And yeah, it sure does. Boy, I'm really curious. Alright, so I'm going to pull off this front section here and see what lies underneath. It's a broken laser. It can't get much more broken. One thing I am going to do, mark it. And indexing parts like this helps, especially when they're optical parts in a resonator, because you want the plate to be at the exact same angle when you put it back on. If you rotate it, there could be minor differences that will set that the optical piece in a resonator off at an angle, and it won't be optimal for the lasing process. So indexing things like output couplers, high reflectors, stuff like that, good practice to get into. Alright, so now we're going to figure out if this is a resonator or if this is a monolithic crystalline assembly. Wow. Okay, so that looks to be high reflector? No, it would be the output coupler, isn't it? Yeah? Yeah, it is the output coupler. Output coupler or infrared window. Wow. There's a lot of stuff going on here. So I've never actually seen this before. So we got this looks to be a purpley filter right there. That's strange. That's very strange. Boy, if that's the vanadate or the yttrium aluminum garnet, that's a very high dopant ratio, but it doesn't look right to be doped. But it could. That could easily be a very heavily doped piece of yag. I don't think it is though. All right, what do we have here? All right, it looks to be the output coupler or an infrared window, the infrared filter. Yeah, that really does. Oh, come on, focus. All right, yeah, so does that block the KTP? Weird. So I've taken a couple of minutes to look over the laser at this point, kind of get a bearing of what's going on. So here's the back section of the laser that has the pump diode. What's really interesting about this particular assembly is that it's off at 45 degrees. There's a little cylindrical lens for output correction here on the front, and what that does is it takes the output of the laser diode and squeezes it down to be more uniform, mostly a square. You'll see this for like fast axis correction, or the use of anamorphic prism pairs to do that output correcting. But yeah, it being at an angle, that's strange. Usually you normally see them fully vertical or horizontal. It's interesting seeing that. But anyway, this has the laser diode in it. That's bad, or says to be bad, which is an 808 nanometer laser diode. And then here in this section right here, is the input to the resonator. Now, as I said, I have never seen a laser crystal that dark before, but that looks to be a piece of YAG with a pretty high neodymium concentration for the dopant, and that neodymium doped YAG or vanadate will take the 108 nanometers and convert it over to 1064. And then after that, we have the front section, which looks to have a couple of different layers. Let's take a look at this in detail. So it has this top little piece of glass right here, which looks to be either some sort of infrared high reflector output coupler for the vanadate or YAG gain medium. It's a 4-level gain medium. And then you have another larger crystal block underneath that, and that could be the potassium titanyl phosphate, the KTP, which is the second harmonic frequency doubler. So yeah, that's what I think is going on. So laser light in 808 here, gets converted over to 1064 here, and then we have the resonator assembly. Either the high reflector for the KTP or the output coupler for the vanadate or YAG, and then 532 nanometers out the other side. So interesting. I guess the next step is to see what the pump diode is, because that is the part that's dead. So looks like there's a screw here on the back which goes up to this one, and then there's 2 screws in the front. I'm going to take off that lens. I still bet it's a C-mount. We're going to find out. Of course, I have 5 Osram PL 530s. So I might just drop in one of those little Osram OPSL lasers inside of this and be done with it. Never getting a new pump diode, because that's easier for me right now. That is a fun weekend project. Oh yeah, that's definitely a C-mount laser diode. Has something on top of it. It's interesting. This thing is definitely worth what I paid for. That's really cool. Let's zoom in on that. Alright, so let's investigate. Oh yeah. Yeah. Okay, so you see the bond wires right there, the gold bond wires. I'll point them out to you. Too high. There we go. So right here you can see these gold bond wires that jump over from this gold tab onto the top of the laser die right there, and those bond wires are completely open. Oh, looks like overcurrent to the pump diode, so that pump diode is toast. You know what I think I'm going to do at this point is I'm just going to try and jump those wires and see if I get any output. Or I can try and do a quick diode check, but I'm afraid if I try and do a diode check, I'm going to do more harm than good. No. Yeah. Let's just do something crude and glob some solder in there and hope for the best, right? Well, that didn't work. Yep, that went well. After looking through my inventory and considering the options that I had as far as this project, I've come up with a good plan of action. So I'm not going to put the original laser resonator back in there or replace the pump diode. I'm sure I'll use the resonator in another project in the future, but not for this one. So I'm going to end up putting an OPSL laser in here, one of the little Osram PL530s. so it's close to 532 nanometers. And here's what I'm going to do to put it in. Well, I found one of these interesting thermoelectric coolers. I have a few of them, and the nice thing is it has a cutout, and that cutout fits over the cutout in the bottom of the laser housing, so that'll prevent any hot spots really building up in that area. A little bit of a divot here, but that shouldn't give me any problems. And the reason why I want to put in a thermoelectric cooler, even though I technically don't need it for the OPSL, is it gives me the ability to temperature stabilize the pump diode inside of the little OPSL laser. There is a PTC thermistor heater on the crystal, so I can set that depending on what temperature the actual laser module is. Of course, that depends on what the thermoelectric cooler is set at. After that's put in, I gotta cut this piece of aluminum to size, and that'll go over the thermoelectric cooler like that. And I have to cut some slots in there, which will let me move the OPSL laser back and forth, and that'll allow me to set my focus with the lenses that are in the front of the laser housing. I'll go over those in a little bit. But anyway, yeah, the cuts will let me slide it back and forth like that and set my distance. I also have to cut the aluminum piece as far as the length inside the laser, not only the width, because I'm going to put one of these little analog drivers in to power the pump diode of the laser. And as you can see, it fits nicely right in there, and will be a good addition. So I'm going to put that in. I'm going to have to modify this so it stays in the laser, but that won't be a problem at all. I'll come up with something. I tend to do so. Now the height with the aluminum block and the thermoelectric cooler is about the right height for the output of the OPSL laser, just as is. Let me try to show you that. Alright, see if you can see it right there. Yep, in front of the OPSL, so right there. So that'll be perfect. And the front lens assembly on this laser housing is adjustable too. So there's 2 screws that I can loosen up, and that'll allow me to change the location of the expanding lens and collimating lens assembly in the front, up and down or left and right a little bit. So that won't be a problem. That'll give me those adjustment points. Now let me see if I can show you the expanding lens and collimating lens in there. So on this side of the front lens assembly, see that there is a concave lens. That is the expanding lens. And on the front we have the collimating lens. So that's nice because I don't have to use one of the OPSL lasers that has an expanding lens built onto it. Here's what they look like when they come out of the Show WX projector. You can see the expanding lens right on the front of that. Won't need it. So that's why I'm going to use one of these. So yeah, you got to make some measurements on the piece of aluminum, and then get that all processed so it plays the function that it needs to. But yeah, that'll go in there quite nice. Those sneaky people at the aluminum fabrication plant thought that they could hide a part from me. Nope. There it was, hiding in the corner all along. Ta-da! So all I did was basically use the reciprocating saw, cut out the corner, and then I cut the grooves in with the Dremel, sanded it. Looks nice. So I think it's time to put a laser together. So grab this stuff right here. Thermoelectric cooler. Let's see, hot side, cold side. Okay, that's the side we want down. And everybody's favorite compound, thermal grease. So go ahead and apply that, and hopefully not make a mess on myself. Oh, and it has begun. Alright, get that mounted in. It's gonna sit right there, and rest on those 2 screws. You'll see when I put this in. Yeah, that's the side I want.
Yep. Alright, looks good.
Oh, is that heat shrink compound on there?
Or heat sink compound. It is. Get off.
Alright. Come on, screws. Parts. This stuff is like Legos for the technically inclined. Alright, tools. Right, so I found these little spacers, and they'll take up just the right amount of slack for the original screws. That way I can use them. Oh. In.
Yeah, we'll put it in
That one. Alright, so the reason why I left this screw out is because I'm going to be mounting down an OPSL laser, so I want a little clip to hold it in place, maybe like this, as I'm epoxying it down, so that way I don't have to sit down and hold it. Let's quickly pair the laser diode up to the laser driver, but first I'm going to go over a modification that I made to the laser driver. You'll see these analog laser drivers on places like eBay, and they're labeled as green, blue, or red, and there is in fact a little difference on the settings of these drivers. So how these drivers work is they have a DC to DC converter on them that steps the voltage from 12 volts down to whatever the output voltage on the DC to DC converter is set at. That's done by a little resistor down here, and they set the voltage depending on what the laser diode needs. So for example, if it's like a red laser diode, they'll usually set the driver around 3 volts. If it's for a blue laser diode, that's around 5 volts. For a green laser diode, usually about 7 to 8 volts. But that setting is important, especially if we want to use these laser drivers for other things. And that has to do with the heat dissipation and efficiency of the transistor here that handles the current regulating portion of the driver. Let's say, for example, you have a driver and it's set for blue. We'll say it's set for 6 volts and the laser diode takes about 5 volts and it runs at an amp. So you got an amp going out and you're dropping 1 volt. So you get about 1 watt power dissipation from that transistor. Cool, that's not a lot. So say if you hook a red laser diode up to it, let's say it takes 2.5 volts, and this is outputting around 6, and you're going to have to drop even more voltage at the same current. So say you're dropping 4 volts at 1 amp. Now that means you have 4 watts going through that transistor as far as the power dissipation, or getting turned into heat. So in order to make this run more efficiently, I made this modification so I can set the voltage close to the operating voltage range of my laser diode, so that way the transistor doesn't get so warm, and it helps a lot. So what I'm going to do right now is I'm going to set the voltage as low as I can. I think it's about 3.5 volts where the DC to DC converter stops operating, but that'll be fine. And the reason why I want to set down the voltage is because the laser diode in here only takes about 1.9 to 2 volts to run. So let's go ahead and do that. Hook up the laser diode driver up to my power supply and lower the voltage. Okay, that's set up. Turn on the power supply. And I'm going to turn up the modulation signal because I want to know what the voltage is set to. And we're going to get the multimeter and we're going to see volts. Okay. So 3.9. That's pretty low. Turn pot tool. Turn pot tool. Alright. Go gadget multi-hands.
Okay, they might drop the voltage down any lower than 3.2. Boy, this is difficult. I need more hands. I'm gonna have to tap it here. I bet I can. I can. Okay, cool. I'll use that. That's easier. Alright, now I'm going to turn the potentiometer on the side that I put in, and we're going to see if we drop the voltage down lower than that. Yep, other way. No, that's as low as it's going to go, it looks like.
Alright, 3.91 it is. Alright, that's off, so we should be getting nothing now. Yep. Alright, cool. Let's get ready to hook a laser diode up to it now. That's down, that's down.
I'm going to turn the current potentiometer all the way down.
That's important. Oh, just a note on these drivers. If you have the currents all the way down and you don't have a modulation signal going in, you won't get any voltage out. So turn this up a little bit till you get voltage coming out of the DC to DC converter, and then you'll be able to set the voltage. Alright, so now we need to set the meter up for reading the current. It never ends. This is what I do for fun. Can you believe this? Like, I mean, I work on lasers for an occupation. What do I do in my free time? Work on lasers. On the upside, I get to keep these lasers when I fix them. All right. And as usual, I'm going to connect the positive side of the laser diode up to the positive side of the driver and do my current, my probes for doing the current reading on the negative side. So go ahead and put that in real quick. Doesn't need to be pretty at this point. Just needs to give me numbers. Okay. I'll get that here. All right, now let's set the current. I'm going to set the current to 450 milliamps. Well, let's go to 450 milliamps. You'll also notice that the OPSL laser will get brighter and dimmer as I'm doing this. Keep in mind, until the PTC heater is temperature stabilized by these inputs, it won't work properly. It'll continue to oscillate as the resonator expands with the heat. So if you see the output dim, or if you see no output at all, don't be too concerned. It's not fully done yet. Anyway, on. Alright. Sortite. I'm going to turn modulation voltage up now. I'm going to put the meter in current now. Alright, that's up. That's good.
Wait, now we can set the current. Alright, that looks good. Looks like we're getting some laser output. It's fantastic. Don't you go higher. So yeah. Alright, so the next step now is to mix up some epoxy and actually epoxy that into place and see if I can get it to be focused as I'm doing that. I'm going to set the focus as it's running. I'm going to have a little bit of adjustment as far as the focus in this plate because I'll be able to move it backwards and forwards, but the closer I get it into focus, the less I'm going to have to move this plate. Of course, I want to have that plate in a good position to line up with everything else. So, yeah, so far, so good. I've just spent a few minutes messing around with the OPSL laser position inside this laser head. And of course, because it's lasers, it turns out to be more complicated than initially thought. Who knew? Anyway, there's two problems. The first problem is that the distance between the expanding lens and color-emitting lens in the front, it needs to be increased because it turns out it's much further back than I thought it would be. So that space needs to be increased. The second problem is that the metal piece that I made puts the OPSL laser just a little higher than I can really get it to get an optimal output position as compared to the expanding lens and the collimating lens, which is giving me a little bit of comet tail. So I have a little bit of paper back here to nudge the laser so it's down like this, which puts me more in the center of the laser output of the lenses. So let me go over what I have now and my solution for that. Why? Oh, here we go. Alright, so it's this length that I need to increase the distance on. So that's one problem. And I really can't go back any further. So I have a couple of options. The first option is I can put another expanding lens in here, but I don't want to. The reason why I don't want to put another lens in here is because this is a very nice laser, very narrow bandwidth. And I want to make sure that I get the least amount of interference out of this laser as I can. And every optic you pass through has internal reflections and will lower the quality of the output. So I'm going to use mirrors instead. So I have this array of mirrors that are pulled from a Casio Slim projector, and I think that I can cut 3 little mirrors out of there, but I only need 2, so I'm going to use the 2 best ones. But I figure if I put the OPSL laser, say, in this corner right here, and I have the laser beam coming out this way, I can reflect it off then on a mirror going this way and then out this way. Therefore, I can double the distance between here. I can also tilt the mirrors to get the laser beam height right for the output lenses, the expanding lens and the collimating lens. So that's my thoughts on it. Let me show you the output beam quality that I have now. It's in a pretty good position. It was in a pretty good position. I think it needs a little bit of a nudge. Alright. There we go. It's a pretty nice output beam. Turn up the power. That line is because a little bit of smudge on the camera. Go ahead and get rid of that. Priorities. Oh, well, that didn't help much. It just changed. But yeah, so nice output if I can get it lined up. So I'm going to get 2 mirrors epoxied in there as well as the OPSL laser. It could be a time-consuming endeavor, but I think it'll be worth it. So first step is to get the OPSL laser epoxied into where I think it will need to be, in that one corner. We'll start positioning mirrors. Continuing on with the general complexity of laser work, I have the OPSL laser head epoxied and set to where I want it to be for the time being. So that's curing. And I have more epoxy mixed up for the mirrors and sections of mirror cut out. So now I have to put 2 little mirrors in and have the laser light come this way, hit one mirror, bounce this way, hit another mirror, bounce this way. So 2 mirrors need to go in. Let's do that carefully. I'm going to turn on the laser. That way I can see where the beam is and start positioning some mirrors. Alright, so got the smaller one first. I really know where they're gonna need to go. While we have the laser on, put some epoxy on the bottom of the mirror there. set that in. Well, it needs to be at that angle. No. That'll do. Nope. Nope. Fail. Man down, man down. Stay. Alright, where is that shooting out now? Alright, I'm gonna move it out just a little bit more. You think my robot voice? Okay, that one looks pretty good. So now that mirror is reflecting the laser beam out that way. You can see the beam right here. Let's see, is that... Yeah, that's pretty good. Pretty good, pretty good. One more mirror to put in. Of course, we're going to have to clean these mirrors off after they get all set, but so far so good. Alright, please don't fall over. Alright, and that one needs to be facing in this manner. Perfect. And now we get to nudge those mirrors around and get it to go out of the lenses. Yeah, you get the general point. I'm going to do all the fine adjustments. We're going to come back to this after the epoxy is set and the mirrors are in. Well, it's been a few hours and the epoxy that's holding the little Osram OPSL laser and those two mirrors should be set. And it's time to see if all the extra effort was worth it. The best way to do that is to initiate flying camera action. Away. And there's the output. Now, I do have a mirror set up in the back of the room, so this is the output from about 14 foot away. And it's a very nice small beam. So here's my finger in comparison. Let's say it's about 3 millimeters, 4 millimeters wide. Very nice round beam. And because it's such a narrow bandwidth, you can see quite a lot of speckle in that beam. The tighter the bandwidth in the laser, the more prominent seeing the speckle is. But that's absolutely beautiful, and that's as round as you can really get. I'm very happy with that. It's a very nice quality laser beam. Alright, so there's a couple of things to do at this point. Docking. Couple of things to do at this point. I'll turn off the laser. I got to install the laser driver now. And to do that, I'm going to put it in this back section. There's just enough room to slide it underneath the spacers. It's actually a lucky coincidence. I not plan on that at all, but it's just enough clearance so that this heat sink fits underneath here. To show you that, I'm going to remove this screw because it does get caught up on the little insert or spacer between the board and the laser driver heatsink. So this guy right here, slide it into position, just like that, and that'll fit in very nicely. You can see what I mean by tight clearances. It just fits. That's nice, very nice. So my idea to hold the driver in is to utilize the screw holes on the bottom of the laser housing. There's two screw holes here, and on this other side there are two corresponding screw holes. So my thought is that I'm going to mark on the side of the heat sink where one of those screw holes is. Probably they're the same size. Yeah, I'm going to mark out where one of those screw holes are, and I'm going to cut into the heat sink, which will give me a notch, and then I'll put two screws in with some washers, and they'll grab onto the side of the heat sink and hold the laser driver in place. I'm not going to do it on camera. Firstly, YouTube won't allow that, and secondly, I'm just kidding. Anyway, I won't do that. I won't do that on camera.
because it's time consuming, noisy, tools, stuff like that. I have to take the whole laser driver apart to cut those notches in. But once I do that, we'll come back to that and get that all locked into place. It's coming together really well. As you can see, the driver is installed and everything is all wired up. I figured, just a simple connector, and there's nothing too important about how that's wired up besides it's proprietary. So it's not like it's wired up exactly like how the laser was originally. So I figured, not important information, and I will enjoy my wiring process in peace. Anyway, let me go over everything that I've done. So I mounted in the laser driver using the method that I thought would work well. In fact, it worked really well. That laser driver is situated in there nice and tightly. I ran a 10K thermistor in this aluminum block here. Of course, that tells me what temperature this is, and therefore I can regulate the temperature of the OPSL laser diode in there too. Let's see. You can see the wires for the thermoelectric cooler underneath that aluminum base plate. That's the negative. Positive is on the other side. Driver voltage adjustment, driver current adjustment, power in to the laser driver, and over here, little white and red wires, that's for my modulation. This purple and white wire right here, that goes up to the little PTC thermistor inside of the OPSL. It's also wired up to the connector and back, and that's how it turned out. So really clean, really nice assembly. It'll go together real well, so I'd say let's do that. And we'll go ahead and give it a couple of tests. I want to see exactly how it performs. Those tests will probably include seeing how much power that I'm getting out of this laser. So I have to run through the temperature of the crystal on the inside of the OPSL laser. And I'll use my laser power meter to do that. And then I want to test the performance against green DPSS laser. It's 532 nanometers, probably against my 543 nanometer green helium neon. I kind of want to see what this is capable of as far as the beam performance. No, go ahead and get this together. Yeah, it looks nice, doesn't it? Looks real good. I think eventually in the future, I actually might print my own label on here and on here, and maybe get these sides laser etched, get the original paint off, and make it my own little thing. But it looks good anyway. And look at this! I have the right tool now. Still not a good tool, but at least it's the right tool. That's it. It's done. But looks perfect on this side. Let's go ahead and plug it in and see what we get for output power. So I already built an adapter that goes in the back. And if this all goes well, we should get green output. We'll find out if it's correctly wired up in a minute. Less than a minute. Alright, so that's power. That's modulation. Alright, see if we get output. We do. Alright, so now I'm going to need to do a couple of things. So first thing is I'm going to need to hook up the power supply to the thermoelectric cooler. Oh yeah, that's right, I'm warming it. I want to put that backwards, don't I? Alright. Now, laser power meter. It's a busy desk.
Alright, on the label it says 125 milliwatts. So let's see if we can get there. I'm going to turn up the modulation. So, of course, we're reading just about nothing on there. I also want to see what the resistance range is for the temperature for the thermistor. So let's see what optimal resistance that is. These two wires right here. 10 ohms. Cool. We're getting there. Would you stop falling off? Come on. Do your job. Alright, so that's the reading of the thermistor on the aluminum block that is both supporting the OPSL. Sorry, distracted by grabbing wires everywhere. Alright, so let's warm up the thermoelectric cooler, see what we can get as far as main output. Warming. Turning up output. So right now what I'm doing is I'm warming up the OPSL, and I want to see exactly at what temperature or resistance here we get the best performance. And so far we have 10 milliwatts. Wow, we're nowhere near where 125 is. Really? Really? 10 milliwatts? 10 milliwatts? Wow. All that work. But at least it's 10 milliwatts of supreme light. After initially only seeing about 10 milliwatts coming out of this laser, I figured, you know what? I'll crank the current up on the pump diode from 450 milliamps all the way up to 650 milliamps. I know that they're capable of handling at least 800 milliamps, but I don't want to push the laser diode too much. Some people have gotten these to go all the way up to like 200 milliwatts output apparently, but yeah, it's weird. The conversion efficiency is not lining up. I should be getting a lot more than 20 milliwatts out. And I played around with both the temperature of the TEC and the temperature of the PTC thermistor on the inside of the OPSL laser. Here's the current resistance on the thermistor that's in the aluminum block underneath the OPSL on top of the thermoelectric cooler. But you know what? Overall, I'm pretty happy. It could be just a matter of that this OPSL laser is a defect, and that's why it never got put into a show WX. Now I want to get a really good idea of just how nice the beam profile is on the Uniphase laser. So I'm going to compare it to another laser that has excellent beam profile, and that is a green helium neon laser right here. It emits a beam that is 543 nanometers, so a little bit towards the yellow compared to the rebuilt Uniphase, but it has a nice round Gaussian beam. As I said, it doesn't really get much better than a helium neon. So let's go ahead and compare the lasers side by side. I got this one blocked off by this little piece of aluminum, so that way I can show you at the same time. And yeah, so there's our two beams. I'm going to turn off the light so you can get a good idea of what they look like. They're about the same power output right now. It's nice and good and dark in here. Alright, flying camera action. Nighttime vision. Okay. So there's the two beams. The helium neon laser is the one that's on the right, and the rebuilt Uniphase is the one that's on the left. But it looks like that I get a slightly smaller beam out of the Uniphase. So the Uniphase is a little lower divergence. Not as round though. You can't really see that speckle, can you? I'm going to try and turn that down.
No, the camera can't pick it up. I'm going to switch to Pro mode so we can get a nice clean look on those beams. Alright, that's a little bit better. Now you can see the difference between those beams a little bit clearer. I'll try and get a better focus on that. Yeah, I know. It's not the right high voltage power supply. Quit breaking out of me. Alright, let's take a look at the beams in general. We're going to need some fog. Don't die in the dark. So both beams are very nice and thin, which is always nice to see. Now I know initially some of you may not be all too impressed because this is not a very powerful laser, doesn't burn or do anything exciting like that, but I guarantee you a narrow bandwidth laser does have some cool things you can do with them. So if you don't have a DPSS laser, if you just have diode lasers, I suggest that you pick up a DPSS laser for yourself and play around with it. As I said, lots of cool things you can do. I'm going to show you one of those cool things. So let me explain what's going on here. Now, the laser is right here. It's shooting out a beam this way, and that's hitting a mirror on the other side of the room, and that mirror is reflecting the output of the laser light back on that white piece of material. Now, there is light coming this way, and then there is light going this way. So we have light that can travel on top of itself, and of course have some interference patterns, and I'm going to show you some of those. And what I'm going to do is I am just going to skim my hair on my arm like that. I'm going to show you what we get. No. Are you ready for this? I don't think you are. But we'll see. Alright, let me all get set up here. Right there. Make sure that the laser is centered. Close enough. Are you focused? It should be focused enough. Alright, here we go. I gotta turn up the shutters. Hold on. Here we go. Let's see how that looks. More laser power. Alright, let's see how that looks. Oh yeah. Experience the interference patterns generated by my arm hair. Enjoy. So here I have the laser bits that are left over. Just out of curiosity, I want to see if the resonator here works still. So I'm going to shoot in some 808 nanometer laser light and see if there's any green that comes out of the front. For that, I have a little 300 milliwatt 808 nanometer laser pointer. I'm going to shoot it in the back, see if we get any green coming out the front. Oh, right away. Wow, that's pretty effective. That is fairly bright. I'm going to turn off the light. Yeah, that's not bad at all. I'm suddenly regretting some life decisions, like putting the OPSL laser in the microgreen. That works really well. Yeah, let's try a quick experiment. So since this has what looks to be a separate KTP, I want to see if I shoot the 808 nanometer laser light into it, if we get something cool, like directly doubled light, which will give us 404 nanometers. So violet laser beam, which would be really cool. Never seen a violet GPSS laser, so if this works, I'd be super excited. Okay. Put that there. Yeah, that'll work. Alright, so I'm going to shoot the same 808 nanometer laser light in here. See if we get anything. I don't think we will. I'm going to need a lens to focus the light down. Alright. See if that works. Does anything. Oh, what? Is green? Wait, hold on. So wait, if that's the entire thing that makes 532 nanometers, then what is that purple crystal? And that must be like some sort of a filter for filtering the 808 nanometer laser light. That's weird. That's doesn't look to be an active component then. Ah, now I have a new mystery. If you know what that purple plate does, let me know. But seeing what I just saw, I think it's for narrowing the band of the pump diode, making it more 808 as a center wavelength. That's weird. I was really hoping that this was going to be a separate doped like YAG or vanadate, because that way I could make a nice little Q switch cavity. But that doesn't seem to be the case anymore. Bummer. I'm suddenly not regretting some life decisions all of a sudden. Well, that's about it for this video. I hope you enjoyed. But before I go, I'm going to do possibly what is the coolest thing you could do with human body hair. So I have the company of my red DPSS and one of my collimated 473 nanometer lasers. So that's red, green, and blue. And we're going to do body hair interference in full color. Yes. I hope you enjoyed watching, and as always, stay tuned for more. Look at that. Look at those numbers. 150 milliwatts. Now it'll do 150 milliwatts. Where was that for the rest of the video? Alright. You know what we have to do. It's officially a burning laser. Woohoo! Woo! Oh, right in the nose. Oh, there's a horrible smell.